to, well, love spheres. You see them everywhere. That perfect little bead of dew on a leaf, right? Or a soap bubble just shimmering away. And then, the massive ones, stars, planets, even atoms, deep down, we sort of picture them as round. Is it all just a coincidence?
It does seem that way sometimes, doesn't it?
Well, today we're doing a deep dive, and it's actually inspired by your really sophisticated creative hypothesis.
Yeah.
You suggested this roundness isn't just about gravity or surface tension like we learned in school.
Right.
But something maybe deeper. You talked about a spherical structure of vibrations coming from a core, kind of like ripples. But, and this is the key part, happening in 4 dimensions.
A fascinating idea to explore.
Absolutely.
Yeah.
So our mission today is to really analyze this. We'll journey through maths, establish science, even some cutting-edge physics to see how your idea holds up. We want to understand why spheres dominate and what it means for your perspective. So, yeah, let's unpack this.
Where should we begin?
Let's start maybe beyond just the physical forces. Think about the sphere as, I don't know, a purely mathematical thing first. Like, does it have special properties that just make it fundamental?
Oh, definitely. And that's a great place to start. You can think of the sphere as this ideal geometric form. It has perfect symmetry. Rotate it any way you like, it looks the same.
Completely uniform.
Exactly. Absolute isotropy, no preferred direction. And, the definition, all points on the surface are the exact same distance from the center. Pure geometry.
Yeah.
And that geometric purity leads to something really practical. For any amount of volume you want to enclose, the sphere does it using the absolute minimum surface area.
Ah, right. Minimum surface area.
And that's key physically. Because systems in nature, they tend to settle into their lowest energy state. For things involving tension or cohesion, like liquids, minimizing surface area is minimizing energy.
So that's why water droplets or soap bubbles just naturally pop into spheres.
Precisely. Surface tension pulls them into that minimum area, lowest energy shape. It's like the sphere is the geometric solution waiting for the physics to catch up.
It's almost like the universe knew about spheres beforehand, doesn't it?
Yeah.
It reminds me of mathematical Platonism, this idea that maths isn't invented, it's discovered. These perfect forms are already out there.
That's a powerful way to think about it.
Yeah, and it makes you think of Eugene Wigner, the physicist, who talked about the unreasonable effectiveness of mathematics, how these abstract ideas just fit reality so perfectly, like Riemann's geometry.
Pure math.
Which was just sitting there, and then Einstein needed it for general relativity, for space-time curvature. It's kind of mind-blowing.
It really is. And what's fascinating here is how the sphere acts almost like a geometric law, a universal template for stability that physical processes just follow. It supports the idea that the universe is fundamentally mathematical, and the sphere is one of its most basic words.
Okay, so we have the sphere as this mathematical ideal, almost like a universal default setting for stability. But let's get back to the physical world. How does this perfection actually get made? And how does this connect to your vibration idea? Let's look at the forces.
Right, let's ground it. At the really big scales, the macrocosm, it's overwhelmingly gravity doing the work.
The big sculptor.
The big sculptor, exactly. Gravity pulls everything towards the center of mass, equally from all directions. It's isotropic. So if you have enough stuff, enough mass, like a planet or a star, gravity just crushes the material's strength over time. It makes it flow.
Until it balances out.
Until it hits what we call hydrostatic equilibrium, a perfect balance between gravity pulling in and pressure pushing out. And the only shape that allows for that perfect all-around balance?
The sphere.
A sphere, it's the lowest gravitational potential energy state. Smaller things, like asteroids, they don't have enough gravity to overcome their own rigidity.
So they end up as cosmic potatoes.
Exactly. Cosmic potatoes. They just don't have the gravitational oomph to smooth themselves out.
I like that. But even the big guys, they're not always perfectly spherical, are they? Rotation messes things up.
That's right. Rotation introduces centrifugal force, which pushes outwards, especially at the equator, so you get an oblate spheroid. Bulging at the middle, squashed at the poles.
Like Jupiter and Saturn. They spin fast, right?
Very fast. Jupiter's oblate by about 6.9%, Saturn even more, around 10.7%. You can actually see it through a telescope.
Wow. And Earth?
Earth is much less, only about 0.3% blate. Venus, rotating incredibly slowly, is almost a perfect sphere, less than 0.0% difference, basically.
But the sun, you mentioned the sun is amazingly round.
It's astounding, actually. Despite its size and rotation, its immense gravity holds it incredibly tight. It's oblate by less than 0.001%. It's pretty much the most perfectly spherical natural object we've ever measured.
That's incredible precision. Okay, so that's gravity. What about smaller scales, like our everyday world?
Right, the mesocosm. Here, gravity's influence on shape is much weaker for small things. Surface tension becomes the star player.
The force that makes water beat up.
Exactly. It comes from the attraction between liquid molecules. The ones at the surface get pulled inwards more strongly because they don't have neighbors on the outside. This creates a kind of elastic skin.
That wants to shrink.
It wants to shrink to the smallest possible area for the volume it contains. And again, that minimum area shape is
The sphere.
the sphere. So little raindrops start spherical. Oil in water forms spherical blobs. Soap bubbles.
Though raindrops flatten as they fall, don't they? That hamburger bun shape.
They do, yeah. That's air pressure pushing against the bottom as they fall faster. But the underlying tendency, the force driving the initial shape, is surface tension, aiming for that sphere.
Makes sense. Okay, macro, meso.
Yeah.
What about the micro atoms? Are they spheres?
The microcosm. Here, shape gets a bit fuzzy, more probabilistic. We talk about electron clouds, their probability distributions.
Right, the orbital shapes.
Yeah, and only the simplest ones, the big orbitals, are actually spherically symmetric. The p-orbitals are like dumbbells, Doogorbitals are more like cloverleafs.
Not very round then.
Individually, no. But in an atom with many electrons, all these different orbital shapes combine. And the overall effect, the averaged out electron cloud, often ends up being generally spherical.
Okay.
Plus, crucially, the electric field pulling the electrons towards the nucleus is spherically symmetric. And the atom, like any system, wants to find its lowest energy state within that field. So the whole atom often behaves as if it's roughly spherical.
So even at the quantum level, there's a tendency towards spherical symmetry, driven by fundamental forces. Interesting.
Such a recurring theme.
Okay, so we've got spheres from math, from gravity, from surface tension, even kind of from atomic forces. But your idea, the listener's idea, adds this layer of vibrations, a vibrational core. Let's dig into that now. Is reality fundamentally vibrational, according to physics? And can those vibrations be spherical?
Well, the idea that reality is vibrational, that actually resonates really strongly with modern physics. Our best description of fundamental reality, quantum field theory, or QFT, it doesn't really talk about solid particles like tiny billiard balls. It talks about continuous fields filling space. An electron field, a photon field, and so on.
Fields, not things.
Exactly. And what we perceive as a particle, say an electron, is actually a localized ripple, a quantized excitation, basically, a vibration in the electron field. So yeah, the idea that everything is vibration is pretty mainstream in fundamental physics.
So that part of the hypothesis fits well.
Yeah.
But are those vibrations spherical? Does QFT say that?
Generally, no. QFT describes the excitations, their energy, momentum, spin, but not usually a specific geometric shape like a sphere for the fundamental vibration itself. That's where your hypothesis lines up almost perfectly with a different, more, let's say, fringe theory.
Which one?
It's called the wave structure of matter, or WSM. People like Milo Wolf have developed this idea, and its core concept is that particles are spherical standing waves.
Spherical standing waves. How does that work?
It imagines a particle, like an electron, as the center of this wave structure. There's an in wave coming in from the universe, converging, and an out wave diverging from the center. They interfere to create a stable, localized, spherical standing wave pattern. So WSM is explicitly spherical and vibrational.
Okay, so there is a theory out there that matches that part. What about other vibrational ideas? String theory? Doesn't that involve vibrations?
It absolutely does. String theory is another huge paradigm based on vibration, but it's different. It proposes that the most fundamental things aren't point particles or spherical waves, but tiny one-dimensional vibrating loops or segments of string.
One-dimensional, like a tiny guitar string.
Kind of, yeah. And the different ways these strings vibrate, their different resonant frequencies or modes correspond to different particles. An electron is one vibration pattern, a quark another, a photon yet another. It's like a cosmic symphony where the notes are particles.
So string theory is vibrational, but the fundamental things are 1D strings, not 3D spherical waves. And doesn't string theory also need extra dimensions?
That's the other key difference, yes. For the math of string theory to work consistently, it typically requires more spatial dimensions than the 3 we experience, usually 9 or 10 spatial dimensions plus time. So 10 or 11 spacetime dimensions in total.
Which is very different from your hypothesis of 3D spherical vibrations
Yeah.
happening in just one extra spatial dimension, making 4 total.
Exactly. Your idea creatively combines elements, the vibration from mainstream physics, the spherical structure maybe inspired by WSM, and then this specific four-dimensional arena. The models really diverge on the geometry and the dimensionality.
Okay, this leads us right to the trickiest part, I think.
Yeah.
This idea of a four-dimensional space. What does that actually mean for reality? How waves travel, how we perceive things?
Right. This is crucial. First, let's be clear. When physicists usually say four-dimensional, they mean Einstein's spacetime. 3 dimensions of space, length, width, height, plus 1 dimension of time, 3 plus 1D.
Got it.
Your hypothesis seems to imply 4 spatial dimensions plus time, a 4 plus 1D spacetime. And a universe with 4 spatial dimensions would behave very, very differently from ours.
Oh, so.
It fundamentally changes how waves travel. This goes back to something called Huygens' principle. The math shows something profound. How a wave spreads depends critically on the number of spatial dimensions. In an odd number of spatial dimensions, like 1, or R3 if you create a disturbance, like a flash of light or a clap of sound, it travels outwards as a sharp, clean wavefront. The wave passes, and then it's gone. Silence. Darkness. The signal is crisp.
Like a ripple on a pond eventually smooths out.
Sort of, but even cleaner. Think of a pluck on a 1D violin string. You get a clear note that fades. But now consider even spatial dimensions like 2 or 4.
What happens then?
If you make a disturbance in 2D or 4D space, the initial wavefront passes, but then a tail or a wake of reverberations keeps arriving afterwards. The signal doesn't end cleanly. It gets smeared out, blurred, echo.
Can you give an analogy?
Think about hitting a 2D drumhead versus plucking that 1D string. The string gives a clear pitch. The drumhead gives more of a thud, right? An indistinct sound that reverberates across the surface. That's kind of like the difference between wave propagation in odd versus even dimensions.
Wow. Okay, so if we lived in a 4D spatial universe,
Yeah.
what would that mean for us?
Yeah.
For seeing and hearing?
It would be a mess. Vision would be a blur. Light waves wouldn't arrive as sharp signals defining edges and shapes. They'd be these prolonged echoing pulses washing over our retinas. You wouldn't see distinct objects.
And sound.
Sound would be just noise, an
Yeah.
incoherent muddle. You wouldn't be able to distinguish pitch clearly or the timing of sounds. Speech comprehension, probably impossible. Complex information processing in general would be incredibly difficult, if not impossible.
So the very clarity of our senses, the fact that we can see distinct things and hear clear sounds, is actually evidence for us being in 3 spatial dimensions.
It's considered very strong evidence, yes. The way waves behave in 3D allows for the stable structures and clear information transfer needed for complex systems, including life and consciousness, to exist.
But wait, doesn't string theory use extra dimensions? How do they get around this blurring problem?
They do, but they handle it differently. The common idea is that those extra dimensions aren't large and extended like R3. They're compactified, curled up incredibly tightly, maybe down at the Planck scale, far too small for us to perceive or for waves to propagate through in a way that affects our macroscopic world.
It rolled up really, really small.
Exactly. Or in other ideas like brain world scenarios, our entire 3 plus 1 dimensional universe is like a membrane, a brain floating in a higher dimensional space called the bulk. But we, and maybe most forces, are confined to this brain. So we primarily experience 3D physics.
So even theories with extra dimensions have ways to avoid the 4D blurring problem for our experience.
They have to, yes, to be consistent with observation. Your hypothesis, placing the fundamental spherical vibrations within a perceivable 4D space where waves propagate, runs right into this propagation problem.
Okay, this really helps synthesize everything. We're looking at your hypothesis, which is this fascinating weave of ideas.
It really is. Let's break down the verdict on its core claims.
Yeah, let's do that.
Okay, first, the vibrational principle. The idea that reality is fundamentally vibrational. As we said, this aligns really well with mainstream QFT and string theory. Strong support there, conceptually.
Good start.
Second, the spherical structure. That these vibrations are specifically spherical. Mainstream theories don't really say this. But the fringe wave structure of matter theory does explicitly model particles this way. So there's a precedent, even if it's not widely accepted.
Okay, so plausible within a specific non-mainstream framework.
Right. Third, the four-dimensional arena. This is the toughest part scientifically. Proposing 4 spatial dimensions for these waves to exist and propagate in seems to directly contradict how we observe waves behaving and the conditions needed for stable structures and clear perception. That blurring effect is a major hurdle.
So the 4D space aspect is the most problematic piece.
It appears to be, based on our current understanding of physics and wave propagation.
But this whole discussion about dimensions, it kind of leads somewhere else, doesn't it? Something deeper.
It absolutely does. It brings us face to face with the anthropic principle, or at least the weak version of it.
Which says?
Essentially, that the properties we observe the universe to have must be compatible with the existence of observers like us who are here to observe it. It sounds a bit circular, but it's profound.
So we see a 3D universe, because if it weren't 3D, we wouldn't be here to see anything.
That's the core idea. 3 spatial dimensions seem uniquely suited for life as we know it. Why? Well, a couple of key reasons. First, fundamental forces like gravity and electromagnetism follow inverse square laws in 3D.
Meaning their strength drops off with the square of the distance.
Right. And it turns out that specific relationship is crucial for stable orbits, planets around stars, electrons around nuclei. In other dimensions, orbits tend to be unstable. Planets would spiral in or fly off. Atoms wouldn't hold together properly.
Wow. So no stable structures.
Likely not. And second, as we just discussed, only in odd dimensions, particularly 3, do you get that clean wave propagation needed for clear signals, perception, information processing.
So no stable structures, no clear information.
It makes complexity, consciousness, and observation itself seem uniquely possible in 3D. So the very fact that we're here, observing stable spheres like planets and stars, is itself powerful evidence for the three-dimensional nature of our space. We see spheres because 3D is the kind of universe where stable spheres and observers can exist.
That's a really powerful conclusion. So the prevalence of this sphere isn't just one thing. It's like layers of truth.
Exactly. It's a multi-layered truth.
It's a mathematical ideal, perfect symmetry, minimum area.
Yes.
It's physically made by forces like gravity and surface tension, working isotropically. Its very stability, and ours depends on space being three-dimensional.
Critically, yes.
And the stuff making the spheres is fundamentally vibrational energy.
That seems to be the picture from our best physics.
So connecting it all, the sphere isn't just a shape. It's like a symbol of how math, physics, and the conditions for our own existence all weave together.
Beautifully put. It's an emergent property reflecting the elegance and constraints of our particular reality. It's the go-to form for stability and efficiency within the rules of our 3D, vibration-based universe.
So maybe the final thought for you, our listener, is this. Next time you notice a sphere, that dewdrop, the moon, even just picturing an atom, think about it not just as a shape, but as this profound clue. A clue to the deep mathematical elegance, the physical laws, and the very specific dimensional conditions that had to be just right for our complex reality, and even for us to exist at all.
It connects the mundane to the cosmic.
It really does. Thank you for joining us on this. Well, this really fascinating deep dive into why the universe is so wonderfully round.